Ach so, ja, nö.
No, it's
Gerne.
okay, it's fine.
Okay. Well, good morning. First of all, I would like to thank you for attending this presentation. My name is Luis Adrián Lizama Servín, and the purpose of my talk is presenting my master thesis, which is the development of a monitoring system for processing the campus data of public transport vehicles. Those are the contents that I will cover during the presentation. I will start talking a little bit of IVU Traffic technologies. I will continue with the problem statement, with the justification of the project, some concepts, the objective of the project, the system requirements, the system overview, the methodology adopted, the system architecture, and I will conclude with the results, observations, and the scope for future work. The project was developed here in collaboration with IVU Traffic Technologies. Therefore, I would like to give a brief overview of the company. IVU Traffic Technologies is a company which offers the proper support and integrated solutions for all kinds of fields in a transport company. These solutions and products are integrated in the IVU suite. For example, can be resource planning, fleet management, ticketing, passenger information, and therefore I would like to give two examples of these products. One example is IVU Real Time, which is the software offered by the company in order to monitor the vehicle departures and vehicle arrivals. It is possible to monitor these arrivals and departures in real time using big displays on the street or using our smartphone, a tablet, or a personal computer. Another example is IVU Cockpit, which is the onboard software which runs on the IVU box, and this software allows the driver to monitor the vehicle timetable as well as carry out the ticketing process. So those are two examples of the products offered by IVU. The problem statement. Nowadays, vehicle monitoring systems are a fast-growing product category due to the large number of companies that own fleets, such as buses, cars, trucks, ships, planes, rails, and therefore there is a strong interest in systems that can monitor, analyze, and store vehicle data. In the particular case of IVU, the project is of great interest to clients in Latin America such as GEP, Grupo Express del Perú. The justification of the project. In this section, it is essential to comment that different companies and different industries have different vehicle data, and therefore they have different needs, and current solutions involve a specialized system for each particular user application. That means that this system represents a particular solution for the clients of IVU. Moreover, the implementation of the system represents a contribution to the management decision-making process for vehicle distance, fuel consumption, and engine temperature. And in addition, the system presents the following benefits. It has an easy integration with the products offered by the company. It has reliable and precise data, and it is a general solution for the entire fleet. Now, I will discuss some briefly concepts that are required in order to understand and to implement the project. First, the campus. Assuming that the car or the vehicle is like the human body, then the campus will be that, such as the nervous system, enabling communication between all parts of the body. CAN stand for Controller Area Network, and it is a multi-master bus allowing communication between electronic control units. Examples of electronic control units can be engine control unit, door sensor, Windows sensor, or just an input or output device. These electronic control units are communicated using the CAN bus line sending and receiving message. These messages are also known as a frames, and the electronic control units are also known as a nodes. So this is the basis from CAN bus. The system adheres to SAE J1939 standard. Therefore, it is essential to know this standard. This standard focuses mainly in the communication between electronic control unit, but of heavy-duty trucks. It defines the physical layer, the data link layer, the network layer, and the application layer of the OSI communication layer. And the project adheres to this standard. Now, I would like to show the hardware used during the system, during the implementation, which is mainly the IVU box. The IVU box is the onboard computer offered by the company for buses, trams, and trains. And well, its operating system is Windows embedded. Obviously, it has a CAN module, which is a CAN controller and a CAN transceiver. It has touchscreen, a variety of interfaces, obviously included the CAN interface, 1 GB of RAM, and it uses industrial grade SD card for mass storage. So this is the hardware used during the implementation. Now I will move on with the objective of the project, the system requirements, the system overview, the methodology adopted, and the system architecture. The objective of the project is the design and implementation of a vehicle monitoring system to retrieve, store, and analyze the CAN bus data. And it has 4 specific objectives. The first one is develop an onboard computer software in order to retrieve the information. The second one is develop a database on the back office system in order to store the information. The third one is develop a service on the back office system in order to extract the retrieved information and store this information on the server database. And finally, develop an online interface to provide access to the information. The following image illustrates the system overview, and I will use this image in order to describe in more detail the specific system requirements. First, the first part consists in develop the onboard computer software which will run on the IVU box. Therefore, the requirements for this software, first, the software should take into account the operating system of the IVU box. Another essential point is that the software should take into account the available memory space. Since the retrieved information from the CAN bus channel will be stored locally on the IVU box, it is essential that the onboard computer software take into account the available memory space. Therefore, it should be defined a proper tool in order to store properly the information on board. This is the first requirement. And obviously the information should be transferred to the back office server. Once the information is stored on the hard disk of the back office server, the next step and the next requirement is implement a service. The main purpose of the service is extract the information retrieved by the IVU box and store this information on the server database. And the system, the service should execute automatically once a day. The next requirement is the implementation of a server database. The server database should store the information properly in order to generate historical data that can be used in the future to generate mathematical models which can be used for predict future events in predictive systems. Therefore, it is essential and important that the server database store the information retrieved from the campus in a proper way. The final requirement is create an online interface. Like I said, the main objective of the main goal of the online interface is provide to the user access to the information in a digestible way. So those are the four specific system requirements, and the image illustrates the system overview. Now I will continue with the methodology adopted in order to accomplish the project. The first step is identify functions and capabilities of IVU box. That means identify or obtain the proper knowledge about the operating system and identify the available memory space. The next step is essential. Select the tool to store the campus data on board. Since the information will be stored also on board the IVU box, it is essential to find a tool which allows the proper storage of the information. The next step is create the onboard computer software. And then the next step is analyze the current back office server. The company offers several products which also have several back office server. Therefore, it is essential to analyze the current back office server. For example, obtain the knowledge about the operating system. Once the server has been analyzed, it is possible to develop a database in the back office server and develop a service on the back office server. And finally, the last step is create an online interface to provide access to the information. The following image illustrates the system architecture, and I will use this image to describe the implementation of the system. As we can observe, there are three main participants: the IVU box, the back office server, and the online interface. First, we have the campus module, which is the hardware which includes the CAN controller and the CAN transceiver, and it is mandatory to create a connection with this hardware in order to retrieve the information from the campus channel. So this is the hardware offered by IVU box in order to create a connection with the campus line. Next, we can observe the onboard computer software. And the main goal of the onboard computer software is create a CAN interface in order to read the information from the campus channel. Once the information has been retrieved, it is essential to store the information locally. Therefore, the onboard computer software implements an embedded database in order to store locally the information. The tool selected to implement this database is an SQLite database, which allows the proper storage of the retrieved information. Once this information has been retrieved, the onboard computer software transfers this database to a special folder called logger folder, and using a telematics gateway, which offers IVU box, the products developed by the company, it is possible to transfer this folder to the back office server. This telematics gateway is offered by the products of IVU, and it is out of the scope of this thesis, but it is used in order to transfer the embedded database to the back office server. Once the information has been received in the back office server, the embedded database is stored on the server hard disk. Then the next step was the implementation of the Windows service. A Windows service enables the possibility to execute long-term applications that runs on the background of Windows sessions. The Windows service, as well as the onboard computer software, were developed using Qt Creator, and therefore the adopted language programming was C++. The Windows service, its main goal is to extract the information from the server hard disk and store this information on the server database. The Windows service can be automatically started, and it is started once a day, and the information is stored, is extracted, and it is stored on the server database. The next step is implement a server database. This database currently is also an SQLite database. However, it is working only as a placeholder. In the future, this database should be replaced for a full database management system such as Oracle. However, the proper organization and the proper storage of the information allows the possibility to create historical data that can be used in the future. And the last part was the implementation of an online interface. The online interface was developed using JavaScript and HTML technologies, and with this web page, the user can create requests to the server. The server is an HTTP Apache server which creates queries to the database using scripts written in PHP language programming. With these instructions, the server obtains information from the database, retrieve the information, process the information, and send back the information to the online interface. In that way, the user is able to monitor and to analyze the retrieved CAM information and to monitor the information that is sending and receiving from the CAN bus line. So this image, like I said, illustrates the system architecture, and this is how the project was implemented. Now, before results and observations, I would like to perform a demo of the system. So I will show you. First, I will start the onboard computer software, which is located on the IVU box. As we can observe, now the onboard computer software is running on the IVU box. The next step is sending CAN bus frames. So, using a special software called PCAM-View and a special hardware called PCAM-Tool, it is possible to simulate a CAN bus line and send the CAN bus frame to the IVU box in order to simulate the CAN bus channel. So I will send frames. And the onboard computer software also presents a filter and a buffer in order to properly read and store locally the information. So currently I'm transferring the frames to the IVU box, and once the information is transferred to the IVU box, an embedded database, in this case an SQLite database, is storing the information. So the next step, I will show you the embedded database. I query the embedded database, I can see the retrieved information. So as you can see, the embedded database stores the information that the IVU box retrieved. This is the information retrieved, and then this information will be transferred to the back office server. And once the information is on the back office server, it is possible to execute the Windows service. For example, this is the Windows service. I'm going to start the Windows service. And once the Windows service is started, the information is extracted and stored on the server database. And in this way, the user has the possibility to analyze and to monitor the information through an online interface. The last section is the online interface, so I will show you the online interface. So this is the online interface. And as you can observe, the online interface has a login procedure, and with the proper credentials, it is possible to access the web page. And now it is possible to define the device number, which is the vehicle number, also define the time period that we want to consult. And once we create the request, PHP scripts are executed in order to retrieve information from the server database. And now it is possible to visualize the vehicle distance regarding the time period that we select. For example, in this particular day, the vehicle distance is that the vehicle travel is 20 kilometers. It is possible also consult the fuel consumption, which is 4 liters in this particular day. Also, the system presents temperature alerts. For example, in this particular day, the maximum temperature has been exceeded by 32 seconds. And finally, the system allows to monitor or to visualize the cost in euros regarding the fuel consumption. For example, in this particular day, the cost in euros regarding the fuel consumption is 42 euros. And as you can see, the system allows to retrieve the information from the CAN bus channel, allows to store locally the information and transfer this information to the back office server, and finally, it's possible to monitor, analyze, and visualize the retrieved information. Now I will return with the presentation. Finally, I can conclude that the implementation of the onboard software, the Windows service, and the online interface were successfully achieved. However, there is some remarks or drawbacks that can improve the system. For example, the onboard software currently is not configurable once it has been deployed. The Windows service, currently the post functionality is currently not supported. And in the case of the online interface, as we can observe, it is able to process only 3 frames: vehicle distance, fuel consumption, and engine temperature. And taking into account these remarks, it is possible to define the scope for future work. So, in the future work, we can define the following proposals. For example, the onboard computer software should be customizable. The Windows service should support change in the directory structure and should include the post functionality. The server database, which is currently a SQLite database, should be changed for a full database management system such as Oracle. And finally, the online interface should be able to process a broad range of CAN bus frames. Currently only support 3. And also, with the implementation of the system, there are 2 more areas of opportunity. The first one is that it is possible to think in a predictive maintenance system. Since the system creates historical data that can be used in the future, now it's possible to think and use this information to create mathematical models which can predict future events. This is the first area of opportunity, and the second area is create a remote monitoring system. Since the current system allows to read and retrieve the information using the proper web service technologies, now it is possible to implement a remote monitoring system to analyze the information, but in real time. So those are two possibilities generated with implementation of the system. A general conclusion, I can say that the system achieved the goals, and it is a product concept that contributes to the products offered by the company. However, there are a lot of areas of opportunity in which the system can be improved. But yeah, that will be my general conclusion, and that's it for my part. Thank you for your attention.
Okay.